Alright, AP Statistics, here is your Chapter 11 multiple choice review. So, we've got a research firm, and they want to know if there's an obvious leader among these 5 manufacturers of laptop computers. They think that they're about equally popular. So they would like to do chi-square test for goodness of fit in order to find out whether that claim is true, or really to see which computer is trusted the most. So we're asked which of the following would be an appropriate null hypothesis for the company to test. And we would never use mean for this type of test, so we can get this one out. The observed counts are all equal to 50. Well, that's not true. Although the expected counts are going to be equal to 50, because if there are 250 people surveyed, if it's the case that people feel that each of the computers are as trustworthy as the others, then we should have them distributed completely evenly. So people in the population are equally likely to identify each of the 5 brands as most trustworthy. Yeah. For at least one of the brands, the proportion of people in the population who trust this brand most is different from the other proportions. That looks like an alternative hypothesis, right? Our null hypothesis is always going to be that this distribution is even, right? That there's no difference. And our alternative is going to be that there is some difference, right? So that one's out. That looks like an alternative hypothesis. The observed counts are equal to the expected counts. That's not it, so we'll choose C and move on to the next one. All right, so same situation. Which of the following are conditions that must be met in order to test this hypothesis using a chi-square test? Each respondent must be randomly selected. Absolutely, it always have to be random. All expected cell counts are at least 5. That is true. The population is normally distributed. Absolutely not. We're using a chi-square distribution, not a normal distribution. So then the answer must be 1 and 2 only. All right. So far, so good. All right, we got the same situation, the same setup. We want to know which represents the component of the chi-square test for Toshiba, right? So remember, our chi-square test is always our observed minus expected divided by expected. So our observed count is 54 minus, and I said during the first one we did, our expected count should be 50, right? So our null hypothesis would be there is no difference in the brand that people trust most. If there is no difference, then that 250 should be split evenly throughout the 5 brands, which means that your expected count would be 50. And you would divide that by your expected count. So we're just looking for the one that matches that. Of course, we're going to take this and square it. Okay. So it looks like we're going to choose D. Okay, we get to do something a little different now. We're wondering if there's a difference in color preference between male and female toddlers. Researchers gave identical toys of 4 different colors to randomly selected samples of male and female children aged 15 to 20 months, and they wanted to know which color toy they picked up first. Here we go. Here are the results. So it looks like we have a 2-way table here. which is the following is the null hypothesis for this test. So we're looking at a 2D table. The distribution, let's just go ahead and read through these and see what makes sense. The distribution of the first choice chosen is 25% for each color, regardless of gender. Let's see. I don't know. The number of observations in each cell is the same for color of first toy chosen. The distribution of first toy chosen is the same for male and female, 15 to 20. I love this one because we're talking about each one of our categories, male and female, choosing color, and we've got that generalized to the population that we sampled from, 15 to 20-month-old children. So I do like this one. All right, moving right along. Same scenario. Under the assumption that the null hypothesis is true, which of the following represents the expected count for male children who chose a blue toy? So remember, from back in the day, we haven't touched on this a lot because we've been having the calculator give us a value. So we haven't been we've been just getting a chi-square value. We've been inputting just some of the statistics in there. So for our expected count, right? So we've been getting our calculators to make our expected count. But for our expected count, reverted, we are going to have our column total times row total divided by grand total. So where will we find that? So we're looking for male children who choose a blue toy. So there's our row total. Here is our, column total. And then the next one is our row total, and there's our grand total. So we're looking for 58 times 116 divided by 236, which is E. All right, moving right along. Same scenario again. The chi-squared statistic for these data is chi-squared equals 8.134. Which of the following intervals contains the p-value for this test? So, you have two options, right? We've been depending a lot on the calculator for this. So, I mean, you could make a matrix with all of these and then get the count for, and then get the p-value for it and see which one is in that interval. It really wouldn't take that long to do. Or if you have your chi-square table in front of you, you can get that out and try to find your probability, or the interval for your probability based on that. So we've done lots of calculator work. Let's go ahead and get out our table and do it that way, because I know that you guys can enter this into a matrix and then get a p-value. So let's get out that chi-square table. All right, so I've got out my chi-square table, and I immediately realized that I need to choose some degrees of freedom. So let's go back and look problem, how do we determine our degrees of freedom? So for a two-way table, our degrees of freedom is going to be equal to our number of rows minus 1 times our number of columns minus 1. So in this case, that's going to be 2 minus 1 times our number of columns, which is 4 minus 1, which turns out to be 3. So we're going to use 3 degrees of freedom, and we're looking for a chi-square value of 8.134. So 3 degrees of freedom, 8.134 is located in here. So we're looking at an interval from 0.05 to 0.025. We choose C. There it is. 0.25. Sorry, B minus. So there we go. The answer is C. Moving right along. For the chi-square test for these data, so we've got a different scenario here. We have some old car brands, really weird, Hudson, Packard, and Studebaker, which are not car brands anymore. I don't know. Yeah, I don't think any of those make them. I think they got absorbed by larger car companies, but that doesn't matter. It's probably not even right. So, you want to know if there are differences in the types of problems encountered by these cars made by different manufacturers. Yeah, so what kind of cars that you drove and identify the first problem that required repair. So here we go. We've got 3 different car brands and 5 different types of repairs. What would be our correct degrees of freedom? We don't need to know any of that stuff. All we need to know is what we did before, right? It's going to be our rows minus 1, so 3 minus 1, times our columns minus 1, 1, 2, 3, 4, 5. So that means that our degrees of freedom is going to be 2 times 4, or 8 degrees of freedom, which is C. Cool, moving right along. Let's look at another one. I believe we're still dealing with these cars. So we'll go through it. We have each chi-square statistic for these data. So what this is our observed minus expected quantity squared divided by our expected value. That's what each one of these individual values in our two-way table are. So we have a little bit to figure out this logical conclusions that we need to make. The first one's not too bad. The chi-square statistic for this test is less than 10. Well, the chi-square statistic is going to be the sum of all of these, which is definitely going to be more than 10. So that one's out. We're going to add those up. We're going to get a number more than 10. The greatest difference between observed and expected counts is electrical repairs for Packards. The biggest difference, the greatest difference. So if I was to take my observed minus expected, if I have a big difference, I should have a large number there, right? and I would be dividing it by my expected, so I should get a larger value if I have a bigger difference. So B is out. The number of observed Hudsons requiring brake repairs is much higher than we would expect if the null hypothesis were true. Observed Hudsons requiring brakes, okay. Observed minus expected is much higher than we would expect if the null hypothesis were true. Now let's come back to this. Because if your observed minus your expected, it seems like that is quite large. Alright, so I like that one, but there might be a better one. D. The observed count of Packards requiring body/cosmetic repairs is close to the expected count. Okay. Packards requiring body cosmetic. That is a fairly low value. If they're close, we should wind up with a fairly low expected counts. With a fairly low x squared individual component. Let's see. Alright, well, I kind of like this one too. Okay. Expected count of Hudsons requiring drivetrain repairs is about the same as the expected count of Studebakers. I don't know how you could get that. Let's see. Repairs. Hudson's drivetrain, Studebakers drivetrain. Absolutely not. Those two values are super different. We're going to count that one out. And now we've got a choice between C and. So I gotta be honest, this one tripped me up a little bit. And then what I did was went and looked, because you see a very large individual component of your chi-square for Hudson, which means that it looks like C is true. And additionally, it looks like D is also true. So we got to do a little more digging, a little more searching to figure out what's going on. And I think if we go back to our next table and we look at our corresponding value for the Hudsons, it's very low. It's much lower. So what that tells me is that what's going on here is that our observed minus expected turned out to be a negative number. And then that got squared, and it gave us a large value in the numerator, which gave us a large value for that component of our chi-squared test statistic. So that means that I'm able to rule out C and choose D. That one was tricky. All right, and so is this one. So for this one, I'm just going to pick a value of our chi-square, and then just see what's true, right? So let's assume let's look at our 5 degrees of freedom problem. for our chi-square statistic. There might be an easier way to do it, but this is the way I was thinking of doing it. So we'll look at 5 degrees of freedom. So not view these things. Well, we're looking at this row. And let's see what's true for values we're looking at between. So we're looking at the probability that chi-square is greater than some critical value for 0.05. So at 0.05, we're at 11.07. So we can just actually plug that in there. Sorry, the little arrows in the way. 11.07. So let's see if any of these are true for 11.07. Well, for 11, so let's assume C equals 11.07. Okay, so let's go ahead and check A. Well, if I multiply C times 2, I get chi-square statistic of 22. If we look at our table, for a chi-square statistic of 22, we're over here. So that probability is actually much less than the probability of just the chi-square statistic being C. So, and this one says it's greater, so that's not true. All right, negative C. Well, this is not true, because if we look at the way this is, right? We're getting probabilities. We're only getting right tail probabilities. So the idea of a negative critical value doesn't really make sense in this context, right? If we're looking at a distribution like this, a negative value does not make sense. In fact, negative chi-square values are undefined. So we're going to go ahead and count out. Okay. For 10 degrees of freedom, the probability is going to be greater than 0.05. So let's go ahead and check that out. Sorry, at 10 degrees of freedom. So let's go ahead and look at that at 10 degrees of freedom. 11.07 would be our chi-square value. So 10 degrees of freedom. Well, a value of 11.7 is going to be a probability much larger. So it is definitely not less than 0.05. It's going to be larger. It's not even on the table, so it's a huge probability. Okay. The probability of our critical value plus 2 is going to be less than 0.05. So, in other words, is a critical value of assuming 13.07 is the probability of that critical value, or sorry, I keep saying critical value because of C, is the probability of that chi-square statistic occurring less than 0.05. So let's look. The probability of the chi-square statistic 13 with 5 degrees of freedom. indeed, right? It's going to be in this range right here, which is going to be less than a probability of 0.05. So far I like this one. Okay. The probability is greater than 0.05 regardless of the degrees of freedom. We have already determined from our work that we did on all the other things that that is not true. So we go with D. And then we follow up with one that's not that. Or finish up, I should say. 3 different ages, 5, 7, and 9. They're given a list of 5 different animals. They ask which one they choose to be. Interesting. They're wondering if the distribution of animal preference is different depending on age. So we got a chi-square test statistic of 13.89, which gave us a p-value of 0.0847. Our significance level, alpha equals 0.05. What are we going to do? Well, of course, we are going to fail to reject the null hypothesis because our p-value is greater than our alpha value. If our p-value was less than our alpha value, we would go ahead and reject the null hypothesis. In this case, we're going to fail to reject, so all automatically just took those out. Okay. There is convincing evidence that the distribution of animal choices is the same. But we wanted to see if there was a difference, right? So our null hypothesis is always going to be that there is no difference, and our alternative hypothesis would be that there is a difference, right? We're not concluding that it's the same. We're concluding that we were concluding that there wasn't enough evidence to say that they are different, right? Which is E. And that concludes the multiple choice review. Thanks for watching.